Right, let's take a look at this starter question here. So this is a link to what we did in the previous two sections. So imagine we had a null and alternative hypotheses, like as follows: 5% level of significance. Find the critical region for this test. Well, one way you might want to do this, instead of going to the table straight away, is you can use your calculator to do this. So we want menu 7. Okay, menu 7, and then if we go down to the next page, binomial CD. Okay, and if we use the list mode, we can sort of generate the table like we have of the probabilities that you saw in the previous lesson. So if you don't know what the critical region is, you may wish to try this. So you can sort of put down 0, 1, 2, 3, 4, 5, 6, something like this in your table. Well, n is the first number that goes in this bracket here, and p is this number. And the p that we're looking at is 0.35. So I could put in 6 there and 0.35. And if you do that, you'll generate a table of your figures. So it has x and p. And what you did is you can just put in these values here. This is what you type into your calculator. And then your probabilities will be listed here on the side. Okay. If we're looking at greater than 0.35, it means we're looking at an upper tail. And the shortcut we said is the first value after the one that goes beyond 95% for the first time. So for me, the value at 4 is the first one that goes over 95%. It's 97%. So that means we're talking about 5 and greater than 5. Okay, this would be the critical region that I was looking at the top end. The actual significance level, you can say what the probability is that's attached with this. Okay. So the critical region they put down is 5 or 6. The reason why they put down 5 or 6 instead of just greater than or equal to 5 is because you can see the end there goes up to 6. Okay, so that one there is just from the book. Actual significance level. So what's the probability of 5 or greater? Well, it's 1 minus the probability of up to and including 4. Okay, so there we go. And as you can see, that value there is definitely less than 5%. What's the actual significance level? Well, it's the probability itself. This is the actual significance level. Okay, we're going to bring all the parts together. So you've seen all of these parts, but we're just going to combine this now. And when we have all of these different parts together, this is what we can call a hypothesis test. So a familiar situation, again, we're flipping a coin 8 times. This is the result that we see. So we're going to say, is this result exceptional or is it relatively normal and so on? He claims it's biased towards heads. So that's about probability. That's about our hypotheses. Significance level 5%. So first thing we do is we define the model and the parameters. So X is the number of times the coin lands heads up. Probability is the probability of this happening. Okay, this is what you want to see. Yeah, this is what we are looking for. What are the hypotheses? Well, again, it's kind of unstated here. If it's a non-biased coin, then the probability would be 0.5. If it's biased towards heads, it's greater than 0.5. So nothing new so far. It's just a case of putting it all together. Right. Use this inequality sign here to let you think about which end we are talking about. Are we talking about the upper end or the lower end? Well, we're talking about the probability above. So we're talking about the upper end. So we're looking down here. So what did we observe? Well, here's our table. And this table, you could generate this on your calculator. We just talked about how you would generate that on your calculator. Okay, you type in 0, 1, 2, 3, 4, 5, 6, 7, 8 maybe. Put these numbers in, press equals, and you'll get these as well. So is the probability of a 6 or more extreme? Remember, we always lump these probabilities together, the result or a more extreme result. So, is this batch of probabilities here, is this extreme enough? Well, what's the probability of what's the probability of a 6 or more? Yeah, what's the probability of a 6 or more? Well, it's 1 minus the probability of up to and including a 5. Okay, and if we do that, 1 minus the probability of up to and including a 5, well, up to and including a 5 is 0.8555. So 1 minus that gives you about, what, about 14, 15%? Okay, gives you this number here. Well, this number here is about 14, 15%, we said. We compare it to the significance level, 5%. So if you've got 14, 15%, that means the thing is pretty likely to happen anyway. It's pretty likely to happen just by chance. So it's not exceptional enough. It's not special enough. It's not less than the 5%. So we have no reason to doubt the model. What we do then is we normally use this phrase insufficient evidence. So there's insufficient evidence to reject the null hypothesis. Okay, in other words, we don't have enough evidence to say that the corn is biased. But these here are the steps that you want to follow. This is the format we want to follow. And I know it seems like all the hard work is being done in part 3, but actually each part here is valid and important as well. Okay? That's one way. That's just one way that we could have done this. You'll notice this didn't talk about critical values or critical regions at all. So we can do this another way that uses critical values and critical regions. So I've just put a note here that I like this method of doing it because you're testing your knowledge of the whole chapter at once. So same situation, same probabilities, same n, all of that's the same. So have a look at how we would do this differently. Well, we define the parameters the same as before. The hypotheses are the same as before. But this is what we're going to do a little bit differently. Instead of starting with this 6 here and having a think, is it exceptional or not, blah, 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 I'm going to think about what values would make me say that the coin is biased. What values would give me, a lump of probabilities less than 5%? Well, if I go to the first value after 95%, this is the shortcut we talked about, it happens at 6. Okay. And then we said that we look at the next value. We look at 7. Why do we look at 7? Well, let me just show you. If we look at 7 or more extreme, that's equal to 1 minus the probability of the thing from before. That's why this trick works, which is 1 minus 0.9648. Can you see that's going to give me about, it's going to be about 3. Let's not write it as a percentage, 0.035, so on. It's going to give me that number there. And if you tried 6 or more, you get 15%, which is clearly not enough. So this is the first case where this probability dips below 0.05. It dips below 5%. It's when it's a 7 or more extreme. Okay, so this is 7 is the critical value, and this is the critical region, isn't it? Greater than or equal to a 7. Well, if you know this is like the red part, okay, that's kind of like the red part from before, and this is sort of like the blue part from before, compare your 6 to the critical value. So 6 is less than the critical value. It does not lie in the critical region. In other words, there's insufficient evidence to reject the null hypothesis. Okay, so the critical region is a 7 or more. How does 6 compare? 6 is not in the critical region, so we do not reject H0. In other words, we say that the coin is not biased, or we do not have enough evidence to suggest that the coin is biased. Okay. Sometimes a question will make you pick one of these approaches in particular. So sometimes a question might say, part A, determine the critical region. Part B, do a hypothesis test. Yeah. So you must know how to do this one. And obviously that was examined in the chapter before. But this is another way that you can do a hypothesis test as well. So really, you need to be aware of both ways of doing it. Finally, you might sort of get like a weird question where you don't have to really do the hypothesis test. It's kind of been given to you already. So Sheila wants to know if a coin is biased towards heads and throws it a large number of times, counting the number of heads. So large number of times. This doesn't give us an n value, right? So we can't actually look up these probabilities ourselves. So the p-value is less than 0.03. So the probability for the thing is given to us. So the probability of this thing is 0.03. Conduct a hypothesis test at the 5% level. So the probability stuff's already been done for us. Somebody's looked it up and they've given us the number. The idea that it happens by chance is 0.03. Well, if you compare it to your significance level, it's less than that. In other words, it is kind of remarkable. It's special. So it causes us to change our beliefs. So we would reject our null and accept our alternative. Okay, that's all we're going to say for this one. It's like all of the probability stuff has been done for us. It's just about the final bit of comparing the number. It's a bit like step 4 only, if you compare to what we did before. Okay, one more example. So the standard treatment for a particular disease has a probability of 40% or 0.4. A certain doctor has undertaken research in this area and has produced a new drug which has been successful with 11 out of 20. 11 out of 20. So are we saying it's more successful or less successful now? Well, 11 out of 20, if you do that on your calculator, it's a little bit over half, isn't it? You've got calculators at A level, we might as well use them. It's 0.55. So the question's starting to come together already. The default position, because it's the standard treatment, standard is a bit like default. So the default position is the P is 0.4. And now if somebody's sort of saying, oh, I've got a new drug here that's more effective, 0.55. So what are they really getting at here? Well, they're getting at my drug is more successful than that, aren't they? That's what they're really looking at. The doctor claims this represents an improvement on the standard treatment. Okay, well, we will be the judge of that, quite literally, with the probabilities that we're going to work out. Test at the 5% significance level the claim made by the doctor. Okay, so let's define the parameters first. So X is going to be the number of successful treatments. Yeah, this looks like this is the successful treatments. So it's binomially distributed. N seems to be 20 here, doesn't it? And the probability, well, we could write it in like this and we could do our hypotheses. We'll do it that way from now on. So the standard treatment is kind of the null hypothesis, that's 0.4. Let's do P equals 0.4. The alternative is that this thing is more successful. Remember, more successful, this one here will let us judge whether to look at the upper end or the lower end when we are, solving this question. Test it at the 5% significance level. So in other words, we need to compare it, this probability that we get, we'll need to compare it to 0.05 and decide to accept or reject. Okay, so I think what we're going to do for this one is, let's start by saying that we're looking at more extreme values. So I think just because I don't have a table and it's at 20, I think I'll go for the first method. So what's the probability of 11 or a more extreme value? Okay, notice that the inequality sign follows, yeah? Well, if I go onto my calculator mode, distribution, binomial CD, variable, let me press the right mode, that would be a good start. Binomial variable. So X is 11. 11, this is your X. N will be 20, and the P, you use the one that's given there as the null hypothesis. So if I do all of that, I get 0.943. Let's round it to 0.943. Actually, I'll do it to 4 decimal places because that appears a lot in mark schemes. So the probability that it's 11 Sorry. The probability that it's 11 or more, we've just used our, what have we done? We've used our calculator mode, which counts the other way around, doesn't it? It counts up to 11. So let's actually just write this out formally. How would we find this? Well, if you wanted 11 and 12 and 13 all the way up to 20, you need to start with everything, and then you need to remove the numbers 1 to 10, don't you? You need to remove these numbers. So let's do that instead. So 1 minus the probability of up to and including 10. So now I actually put that into my calculator. So if I put 10 in, I will get 0.8725. Okay. And then I need to do 1 minus that. Sorry about that. I think my brain seemed to switch off a little bit. So if I store that value into my calculator, go back onto the normal mode, 1 minus the value that I've stored there. So I get an answer of 0, let's get that one out of the way, 0.1275. In other words, there is a 12, almost 13% chance that 11 or more people would be cured just by chance. Well, how does this compare to the 5%? This is significantly bigger than the 5%. So in these situations, we actually just say, well, we accept our null hypothesis, okay? And then what you would say is you'd say there's insufficient evidence to reject, okay? So if you want, intuitively, what's happening here, the chance that 11 or more people would get cured if the probability of the drug was the same, it's about like 13%. So if it's 13%, it's pretty likely to happen. If it's pretty likely to happen, you cannot conclude that anything special is going on here, that there must be something unique and amazing about this thing, because it had a 13% chance of happening. So it's pretty likely that that thing will just happen anyway. That's kind of how the question works out. Right. So last question here on the board for you to have a look at. I'll give you a hint here at the top and a hint at the bottom. And I recommend just pausing the video quickly and having a go. Okay, so if you haven't already paused the video and had a go, please make sure that you do. Let's take a look then. So the probability, so the null hypothesis is zero, that probability is 0.2. That's because if there's 5 possible choices, A, B, C, D, E maybe, and you're guessing, you have a 0.2% chance. Yeah. This is the student is just guessing. Well, what's the alternative? Well, the student has done better, haven't they? They got 4 correct, 4 out of 10. So 0.4. So that suggests that the inequality that we're looking at is like this. Okay, this suggests that the alternative hypothesis is a bit like, you know, the student is better than what the teacher is thinking. That's pretty much kind of what that means. Well, that's that part there. You get your mark. Write this out. So x tilde b is fine. 10, 0.2, or you could leave p in there. Okay, that's your other mark. So the student got 4 questions correct. Well, what we do is we say, you know, from the inequality, we're looking at this end. So we're looking at the upper tail, and we need to look at 4 or more extreme. It's always or more extreme. How do we find this? Because the calculator counts up, it has the inequality sign the other way. Well, if we don't have a table, we do this on our calculator. Okay. And this will give us, you know, 12% effectively. 12%, it's much bigger than 5%. So when we have these situations, we accept the null hypothesis. Okay. Insufficient evidence to reject. In other words, we accept. That's what that means. An alternative approach, and you should make sure that this makes sense as well, probably use the list mode on your calculator to do this one, is you would find that the critical region is values of 5 or more. Okay, values of 5 or more. And 4 is not in that critical region. So in other words, we'd still accept the null hypothesis. So these are the two different ways that you could have answered the question.